In this video, we're going to look at the different types of loads that we're going to put on our beams. Now, we are going to focus on 4 main types of loads, but in theory, we're going to learn how to deal with any possible load you want. We've seen little bits previously how if there's a load you haven't got a formula for example, that you can use curve fitting techniques to come up with a formula for it. And later on, when there's no formula for the load, when it's kind of too complicated, we're going to come up with numerical techniques. So you can well, we're only going to go as far as this year, but the idea is kind of generalized. Okay, so 4 main types of loads. The first is uniformly UDLs over the entire beam. Now I might actually call these also constant loads. So the load is the same over the whole of the beam. Constant is probably what I would go for. The problem with UDL, we're going to learn how to write down a formula for UDL, and if you use that formula when the UDL is over the entire beam, you make the question far harder than you need to. Much easier just to call it maybe a constant load. So we'll draw a picture. What the actual what's going on with the ends is not actually important, how it's set up. So I won't actually draw those. So now I'll show you how you would probably draw this. You'd probably do this kind of business. And this is how I'll do it as well. So all these should be at the same height because the load per unit length is the same over the entire length of the beam. If it was me drawing this, I'd probably just do that. But I'll go with this thing. But you need to understand these circly things mean this, that the load per unit length is the same over the entirety of the beam. So mathematically, what you do here is just say that the load per unit length is W0. So this is W0 kilonewtons per meter. It's the constant value of the UDL. So for example, if it was 18 kilonewtons per meter over the entire beam, you would just take W of x equal to 18. Okay, so let's do a little example here. Find the bending moment due to a UDL of 36 kilonewtons per meter across a beam of length 7, where it says that the bending moment at 0 is 0, and the derivative of the bending moment at 0 is 126. Now we will learn, well, you don't have to learn off these formulas, by the way. They'll always be given to you in this module. Well, it's open book anyway, so there's no formulas to learn off. But I might just note that this is the same as the shear at 0. As you'd expect, because the 36 kilonewtons by 7 is 252, and we're going to learn that the reactions are going to add up to the total load. So if this is a symmetric beam situation, so the two reactions are going to be the same, and they must add up to that number I mentioned there. So divide them by 2, you get 126. So that's what's going on there. Okay, so the differential equation that governs the relationship between the bending moment and the load per unit length is that the second derivative, which I could have really written as m double dashed, which I'll probably do for space, is minus the load per unit length. And here we're talking about a constant load of 36. So minus that would be minus 36. Okay. So now we're going to anti-differentiate both sides. So if you anti-differentiate the second derivative, think about the original function is m of x, differentiate it to get the first derivative, differentiate against the second derivative. It might be worth just writing this on the side here so everyone is clear. So start with the bending moment. If you differentiate it, you get the first derivative. And if you differentiate again, you get the second derivative. And let's call this just d. Now I mean differentiate with respect to x, and d differentiate with respect to x. So to get from the second derivative, as we have, back to the function, you must anti-differentiate twice. Now let's write d inverse, and the d inverse really means you anti-differentiate with respect to x. Okay. And now if two things are equal and you anti-differentiate both of them, they will remain equal. So the antiderivative of the second derivative is the first derivative. And now think. So if you differentiate this, you get this. Differentiate what to get minus 36? What is the antiderivative of minus 36? It's minus 36x. Now, imagine if you're going back. You differentiate this, you get the first derivative, you get the second derivative. Good. You differentiate the minus 36x, you get minus 36x. That's good. But there could actually be something else here. There could be a constant here, which we will call, for the moment, call C1. Okay. And now to get the bending moment, we anti-differentiate a second time. So anti-differentiate both sides of this. So we get the antiderivative of the first derivative is the original function m of x. Now we're going to anti-differentiate term by term, fixing constants. So I'm going to fix the minus 36. And now the question is, what is the antiderivative of x? Now I would suggest maybe think about x as x to the power of 1. And how do you anti-differentiate powers of x? You add 1 to the power, divide by the new power. And then what would you have to differentiate to end up with c1? Well, it would have to be c1 times x. And then every time you anti-differentiate, you must pick up a constant, so a second constant, c2. So this here is the bending moment at any point x along this beam. If we have extra information, as we do here, that the bending moment at 0 is 0, and the derivative of the bending moment at 0 is 126, you can find those two constants. It's worth saying that if this beam was simply supported, you certainly would have this situation. When a beam is simply supported, so maybe something like this, there's nothing stopping the beam. This doesn't actually cause the beam to bend. The beam is happy enough just doing whatever it wants. The bending moment there is 0. If the beam was fixed ends, you'd have a different story. So here's simply supported. Fixed ends is more like this. And you see the way the thing on top causes the beam to bend? That's a bending moment. So if you fixed ends, the bending moment at 0 is not 0. Simply supported, we will all be covering this, the bending moment is 0. So the first thing is to do this, it's called a boundary condition, something going on at the ends of the beams. So if I do it here, if I substitute in x equal to 0, which is what this means, I get out 0. So if I substitute x equal to 0 into this, I get out 0. So sub in x equal to 0 here, 0 squared over 2, that's gone. Sub in 0 here, c1 times 0, that's gone. I'm just left with c2, and that must equal 0, so I end up with c2 is equal to 0. We'll do more of these in time. Then it also says that the derivative at 0 is 126. So if we plug in x equals 0 into this, we get out 126. And if you plug in 0 in for minus 36 times 0, you just get 0 plus c1. So the derivative at 0 is c1. And that must be equal to 126, so the c1 is 126. And now we put this all together. Minus 36 divided by 2 is minus 18. There's the x squared. c1 is 126 times x, and c2 is 0. We leave that out. So you found a formula for the bending moment at any point on the beam. And we might just show here in particular, at the end of the beam, the way this is set up. So it's a length 7 beam. So at the other end of the beam, what is the bending moment? I plug in 7 into that. So minus 18 times 7 squared plus 126 times 7, I get out 0. And what that means is that the beam is also simply supported on the right hand side. So it's simply supported on the left and simply supported on the right. Okay, the next thing we consider is a UDL over some of the beam. Okay, so this looks, I'm going to draw again a beam without supports. Again, now, well, the way we're going to do it, this will be, let's put in some axes. So we won't worry about the fact that the support might be in there rather than there. We'll just assume it's on the end. This would be, for example, L, the span of the beam, for argument's sake. And suppose we want a a UDL of magnitude W0 between x equal to A and x equal to B. So now we're going to draw this. Actually, I'm going to do something a bit different. So this is something that's 0 here, and is equal to W0 between A and B. Now you won't draw it like this, but this should remind you of the Heaviside function, the unit step. Now you're probably going to draw it like that instead, but it's actually the 0, W0, 0 is actually what it should be. And if you look back at the previous videos about the Heaviside function and that step functions, you'll see that the appropriate thing is you need something that's equal to 1 between A and B and 0 elsewhere. That's that thing there. So this bit is equal to 1 between A and B. A and B are some prescribed distances along the beam, say 1 meter and 3 meters. So you got a UDL between 1 and 3. And it'll be 0 elsewhere, which is what you want. And so just multiply this number 1, this thing that's equal to 1, by the load per unit length that you're actually interested in, and that will do it. So it ends up being W0 times, if you multiply this out, W0 times turn on minus W0 times turn off. So the language we might use here is turn on, turn off. So let's write turn on the UDL at A and turn it off at B. Okay. So a little example here. So write down the load, W of x, due to a UDL of 18 kilonewtons from x equal to 2 to x equal to 3 meters on a beam of length 5. We're going to draw a picture of that. And then now find the bending moment due to this load. Write your answer in terms of MA, the bending moment at x equal to 0, and RA, the shearing force at x equal to 0. Okay, so we're going to solve this differential equation eventually, but we have to write down W of x first. So I think the best thing we do is maybe draw this picture and then write down what the load per unit length is. So let's draw our beam. And now again, we're actually not specifying what the supports are here, so I won't draw them. X goes from 0 to 5. That's x. And now we're on this axis, we're going to draw W. So between 2 and 3, which is, say, if this is 5, let's say between 2 and 3, I don't know. It's probably, there, look, it is what it is. 2 and 3, there's a UDL of magnitude 18. Now I'm going to start drawing your circly things, but really remember it's more actually like a step. 0, 18, 0. Something like that. And the magnitude of it is, what did we say, 18. Okay, so what we do is we'll turn it on and then turn it off. So W of x equal to. Now we can't, so so I was saying before with the constant load, you could turn it, like you could turn this on at 0 and off at the length. It'd be stupid. Why would you use these complicated Heaviside functions when you can just use 18? Okay, but here you do need the step function. So we'll turn it on at 2, so that's u of x minus 2, and turn it off with a minus 18 times u of x minus 3. Okay, now what we're going to have to do now is solve the equation that the second derivative of the bending moment is minus the load per unit length. Now I would prefer that you turn on and turn off and write this down and then get the minus w of x. Now how do you get from w of x to minus w of x? You multiply by minus 1. And what happens if you multiply both sides of this by minus 1? So let's just multiply by minus 1. You get your minus w of x. And now look what happens. You'll get minus times this is minus 18 u of x minus 2, and then minus times minus is plus plus 18 times u of x minus 3. So you see that the signs change. Now I'd be recommending that you write this down and then write this down. Now you might skip this particular line, but I recommend writing this one down, because we're going to have a different thing later on where there's like a plus plus pattern becomes a minus minus, and rather than getting confused, just write down the load per unit length properly, multiply both sides by -1. So now let's write down the bending moment equation. It says that the second derivative of the bending moment is equal to minus the load per unit length, which is this. Now we need to anti-differentiate. Now I probably need a bit of paper here just to write something down. Will I have space for it? I'll have space over here. So what we need to get is the kind of the pattern of the antiderivatives with these step functions. So the way it works is, if I come over here, so if you start with a delta function, now delta functions are nothing to do with point loads necessarily, but we'll include them here. So if you anti-differentiate this, so the inverse is the anti-bit, anti-differentiate, you get a step function u of x minus a. And this is equal to 0 before a, equal to 1 after a. Then you anti-differentiate again, you get square brackets. You have to get square brackets. Now what does the square bracket do? If you give it something negative, it gives you back 0. In other words, if the thing in the square bracket is negative, the square bracket of a negative is 0. And if you give it something positive, it gives you back the same thing. Then you anti-differentiate again. Now the square brackets anti-differentiate just like powers of x. So in particular, this is like to the power of 1. And so if we anti-differentiate this, we'll add 1 to the power and divide by the new power. And you keep on going, but I'll recommend that you, what I call fix the constant and anti-differentiate. Dividing by 2, here's the constant. Dividing by 2 is halving. Dividing by 3 is multiplying by a third. So dividing by 2 is multiplying by a half. So I'm going to fix that half. Okay. And then what will the antiderivative of the square bracket squared be? Add 1 to the power, divide by the new power. Okay, that'll do us for now. Okay, so just so you remember symbolically anyway, what will the antiderivative of u be? Square bracket. Right, so we've got the second derivative here. If we differentiate it, we get the third derivative. We want to go the other way. We want to anti-differentiate. So maybe I'll start writing some of these underneath here. So this d inverse means I'm anti-differentiating. Okay, antiderivative of the second derivative gives you the first derivative. Term by term, fixing constants. Fix the minus 18. And the antiderivative of u is square bracket. Now, you have to use the square brackets. You can't, because they mean something in particular. Square bracket x minus 2. Plus, fix the constant 18. U antiderivative is square bracket. And anytime you anti-differentiate, you must pick up a constant. And we go again. Anti-differentiate a second time. The antiderivative of the first derivative is the original function m of x. Fix the constant, anti-differentiate term by term. So fix the minus 18. And remember that these square brackets are like powers of x, they're to the power of 1. And it has to go outside. So this has to go outside, definitely. Because if the square was inside here, if you had x minus a all squared, then the thing inside the square bracket will always be positive. Whereas it's supposed to work like if the thing inside the square bracket is negative, it gives you 0. So antiderivative of square bracket to the power of 1 is square bracket squared over 2. I'm going to tidy this up. Hopefully we've space for some more. Fix the constant 18. Antiderivative square bracket is square bracket squared over 2. Plus antiderivative c1. Well, we should be starting to get used to this. So what would you differentiate to end up with c1? It would have to be c1 times x. And we're always going to pick up a constant every time we anti-differentiate. So the other constant here is c2. Now we'll just tidy this up. Minus 18 divided by 2 is 9 and 18 divided by 2 is 9. Well, the first one obviously being minus 9. So you get that the bending moment on this beam due to this UDL between 2 and 3 is minus 9 square bracket x minus 2 cubed. Where am I going with cubed? Squared plus 18 divided by 2, 9 square bracket x minus 3 squared plus c1x plus c2. Right. So if we now know stuff about, actually what we're doing now is we're not saying we know anything about the supports, but they're telling us that MA is the bending moment at x equal to 0. So that means that MA is bending moment at x equal to 0. Because that's what this m of x means. It's the bending moment at x. That's what this w of x means, the bending moment at x. Sorry, the load per unit length at x. And it's also telling us that the shearing force, now the RA is a bit harder, the shearing force at 0 would be V of 0. But if we go back to, it might be the previous lecture, the shear force is the derivative of the bending moment. So the shear force at 0 is the same as the derivative of the bending moment at 0. And we're saying that this is RA. So we're going to replace m of 0 with MA and m dash of 0 with RA. And what we're going to learn actually is that the first constant here is RA and the second constant is MA. And pretty much all the time that's going to be the case. So we're going to stop writing C1, C2 here. We're going to write RA, MA. Okay, so let's do it. So now apply the boundary conditions. M of 0 is equal to MA and m dash of 0 is RA. Right, let's see what we get. So if I do m of 0, so I want to be clear here, what I'm actually doing is I'm substituting in x equal to 0 into this. Okay, so I get minus 9 square bracket, 0 minus 2 is just minus 2, square bracket squared, plus 9, and go again. So if I put a 0 in here, I get 0 minus 3, which is minus 3, plus c1 times, I'm putting in x equal to 0, c1 times 0 is 0, plus c2. And we're saying that the bending moment at 0, which is equal to this, is also equal to, we're just going to call it MA. So these things are the same, this equal to this equal to this, and so these two are the same. And now what do you see? Well, what's square bracket of a negative? And by the way, this isn't something on your calculator, it's only for really engineers use this. Square bracket of a negative is 0, so that's gone. Square bracket of a negative is 0, and it doesn't matter that you square it because you're not squaring the minus 3, you're squaring the square bracket of minus 3, you're squaring 0, which gives you 0, that's gone. And obviously 0 doesn't contribute anything. So this C2 is equal to MA. And this is going to always be the case. This second constant, if we're anti-differentiating from minus load per unit length, is going to be, we're not going to write C2, we're going to write MA. Similar story, let's substitute in x equal to 0 into this. So, into the derivative now. So this will be minus 18 times square bracket of 0 minus 2, which is 0. No, it's not. The square bracket of minus 2 is 0, but I want to write in the minus 2. Plus 18. 0 minus 3 gives me minus 3. Square bracket of minus 3. Plus C1. And we're told that this m dash to 0 must be the reaction at A. Now, same as before, the square bracket of a negative is 0. Square bracket of this is 18 times 0, that's 0. So this C1 is, in fact, RA. And so our answer is minus 9 square bracket x minus 2 squared plus 9 square bracket x minus 3 squared plus not C1 times x, but RA times x, and not plus C2, but plus MA. So, what are we going to do now? So note that when the UDL continues up to the very end of the beam, So if it goes, say, from 2 to 6 on a span 6 meter beam, there's no need to turn it off. So we'll just explain why that's the case. And that'll be the end of this lecture. So take our beam, we won't say anything about the supports. We will say that it has a span of L, we'll do that. This axis is the load per unit length. This axis is the distance along the beam from the left hand side, from 0. Okay, so what we're talking about is, say if we had, this is the length 6 beam, a UDL between 4 and 6. So you draw your UDLs like this. You want the height of them to be the same, those little circle yolks, and it's 32 kilonewtons per meter. Right, so what I'm saying here is if your UDL goes to the end of the beam, there's no, you don't have to turn it off, right? So whether you take this or this, so this is turning it on and not turning it off, and this is turning it on and the minus turning it off at 6, you get the same answer. And the reason this is, the only values of x that you'll consider are between 0 and 6. So if you take any value, now so the biggest value is 6. Now the u of 6 is actually equal to, so if you put u of 6 into this, you get 32, but so you get 32 at 6, and this one will give you 0, but you learn that a single point actually doesn't really matter. Really what you're interested in is points that are smaller than 6. And if you take anything that's smaller than 6, for example, x equal to 5.5, this bit is always going to be 0. So at x equal to 5.5, minus 32, u of, say, 5.5 minus 6, and this 5.5 minus 6 is minus a half, so this is minus 32 times u of minus a half, just something negative. And the u thing, if you give it something negative, it gives you out 0. If you give it out something positive, it gives you out 1. Give it something negative, it gives you out 0. So for any point of interest between 0 and 6, this thing's equal to 0. So there's no need to turn them off. If you do turn it off, so if you use this instead, your answer will be correct, but you'll just have more writing than you need.